Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this lecture, we are going to implement Deep Q-Learning in TensorFlow for Breakout. Since we've already implemented Deep Q-Learning for CardPool, all that's really required here is that we're changing the network from a feed-forward neural network to a convolutional neural network, and we're stacking multiple observations to create the state. If you don't want to try to code this yourself, although I highly recommend you do, the relevant file in the course repo is dqn_tf.py in the subfolder Atari. So at the top we have all our usual imports. Next we define image width and height as constants. This will be used for downsampling the images and for defining the shape of the input for TensorFlow. Next we have the downsample image function. It takes in an image, crops it, scales the values to be from 0 to 1, converts it to grayscale, and then resizes it using nearest neighbor interpolation. Next we have the DQN class. Most of the changes here will be in the constructor. Notice how we no longer have to specify D, because we know the image size, and we have to add the convolutional layer sizes as an argument. Notice how we're also passing in the scope as an argument. This is just a string that allows us to declare a scope for all the variables we are about to create. The main reason we want to do this is because it's going to give our variables unique names with common prefixes. Next, we declare the inputs and targets. This is mostly the same as before, but now x is a 4-dimensional tensor. This function is now simpler than the previous Deep Q-Learning script, because we no longer have two separate sets of loops for creating the layers and calculating the output. Instead, we can do this all in one step. The contrib module also contains a useful flatten function, which doesn't require us to specify the size of the second dimension. After this, things are mostly the same as before. In this script, I've used an alternative way of storing the experiences, which is perhaps more intuitive, a list of 4 tuples. You'll see how we can split up the tuples later. Next we have the copyFrom function, which is similar to before, but now we don't have a params variable to use. Instead, we need to loop through all the trainable variables TensorFlow knows about and choose the ones that start with the prefix given by the scope we set earlier. After that, the actual copying is the same. Next, we skip over to the train function, which is now different because the way we've stored the experiences is different. First, we can make use of the built-in Python random module to take a sample from the list. Next, we need to separate the tuples. We can use zip for this. We then map each list of tuples to NumPy arrays, since they are most useful in this form. Finally, we create the targets and call the train op. Next, we have the add experience function. Notice how it's a lot simpler than before, since we can just append the tuple itself. Sample action is the same. Next, we have the update state function. This takes in a state, which is a list of observations of size 4 or less, and a new observation. It appends the observation to this list, and then removes the first observation if the size of the list is greater than 4. Remember, this is because we represent the state as 4 stacked consecutive frames. Next, we have the play1 function. This is a little more complicated than before, but only because we now have to worry about stacking frames to build the state. Before the loop, we add the initial observation to the state. Once we're inside the loop, we need to take an action. But we don't have a full state matrix to pass into the model for the first 3 iterations, so all we do is sample a random action. Next, we copy the most recent observation to the previous state list. This is analogous to copying the observation to the previous observation in our earlier code. Next, we perform the action and then add the resulting observation to the state. Next, we update the rewards, call train on the model, and then update epsilon. Remember that we are now using a finer grain detail on the epsilon update, decreasing it linearly until we hit 0.1. Finally, we check if we should copy the main network over to the target network. Next, we have the main section. This is mostly the same as before, except we have some additional hyperparameters, specifically the convolutional layer sizes. Other than that, nothing in here should be unexpected. Let's run this and see what we get.